All right. Okay, so if you just go to for example Wikipedia and search for Gauss quadrature, you're gonna see it tells you a pretty comprehensive table of what the points are and what the weights should be. So for example, when the number of points is just 1, right? I'm trying to approximate an integral with just 1 point. It makes sense that you should choose the point to be right in the middle of the domain, which is basically from -1 to 1. Of course, if you apply this to an integral of other domains, you're going to be scaling it with the half size of the domain and shift it to the center of the domain, right? But like the default, when the integral is from -1 to 1, then you want to use the point of 0. And the corresponding weight is equal to 2, which is really the width of the integral you are integrating. Okay, and when you have 2 points, it's interesting that what you should be taking is plus minus 1 over square root of 3, and the weights, of course, should be 1 because you have 2 points. Each point has a weight of 1, so the total weight is equal to 2, right? And you should be getting a total weight of 2 always, because the width of the integral is equal to 2. And that means if you integrate a constant function of 1, you should always get the width of the domain, which is 2. All right, and as you add more and more points, you have a bunch of increasingly complex distribution of points. And in MATLAB, there are functions you can use to calculate the values, the points, and the weights for higher order Gauss quadrature points. But the point is, you will never need more than a few nodes for Gauss quadrature if you have a smooth function, because Gauss quadrature actually converges extremely fast as you increase the number of points. Okay. For the kind of functions we are looking over here, usually 2-3 points are more than sufficient to get you an extremely accurate integral for this kind of functions. And not only it is useful for computing the right-hand side, which is the integral of the test functions with f, it is also very useful in computing, for example, d phi dx, and d phi j dx. You may ask that in our case, all of them are constants. So what's the point of using something more complicated? Oh, the point is that if you use more advanced finite element methods, then the phis are no longer going to be linear functions, and the derivatives are no longer going to be constant. So in these cases, it's becoming increasingly a good idea to use Gauss quadrature to compute essentially all kinds of integrals that is going to appear in finite element methods. All right, so that's one of the things I just want to go over with you, because if you look at any finite element solvers, you're going to be seeing Gauss quadratures all over the place. Any questions on this? And this is, again, something quite useful in general for numerical methods, not just for finite elements or PDEs. Whenever you want to integrate a smooth function and the integration analytically is too complicated, or you are just too lazy, use Gauss quadrature, right? You get extremely precise answers with just a few points. Okay, questions on this?